Well, good afternoon. Thank you for coming to this introduction to Stacc. This is a core calculus that I've been developing for FP languages. Core language, it's a minimal foundational meta theory for the language. So examples are system math for Haskell, Idris core as well. So the core languages for those languages. And this is one that I've been developing, and it has the particularity that takes the unorthodox approach of not being based on the Lambda Calculus. So why we are in LambdaConf? Why not Lambda Calculus? Isn't all we need Lambda? All you need is Lambda? Well, I find as a practitioner, FP practitioner in the software development industry for a long time, so I'm not coming from academia, and my interest in type theory is quite recent. But I found that anybody approaching to what's the foundational theory in FP languages first gets exposed to the Lambda Calculus, and then gets exposed to the final language. Imagine Idris for dependently typed, and that's quite a wide conceptual gap. Why it's in between from just function to all this syntax, all these things. Obviously, there is an effort in education. I think that there have been great talks explaining the internals of GHC, and you can learn about it, but I don't know, for somebody outside academia, I found it quite heavy. So I think also that elevating the foundational theory, being a bit richer, slightly less abstract, gives us some cohesion in the calculus, and it can basically help with some constructs. So the idea, another goal was to make it very approachable. So it uses the notation is quite familiar for anybody with math, basic math or set theory background. So let's see what's Stacc. Well, it's set theoretic base, algebraic, and constructive. Set theoretic because the main building block of the calculus is the set of predicates. That's basically in line with the propositions as types. We'll see more about that in a moment. And also, as I said, the notation and semantics, it's rooted in set theory. For instance, application, it's set union. We'll see examples of that. But the ST could also mean structural. Maybe could make sense as well. It's work in progress, so I might change it. But structural as in a structural typing. And yesterday in the keynote, we had a taste of what the structural typing can give us in Mike's keynote. And also we'll see what properties structurality gives us. Algebraic, and yeah, sorry, just to finish with well, algebraic as in opposition to the Lambda Calculus, which only has product and application. Application is the abstraction in X, and product is basically the body of the abstraction. It's a product of terms in the body. So I think Stacc, it's a bit richer than Lambda Calculus. So in the basic meta theory, it also has coproduct. So that's why I'm naming it algebraic, because it has both dualities of the product and coproduct. And what the coproduct gives us is conditional values. We'll see there disjoint union, which could be another name for a coproduct. We see an example of the syntax, which is basically we create an equivalence between a variable b that could be either 0 or a, depending on a condition. But we'll go into more detail about this. And finally, constructive, inspired by intuitionistic type theory by Per Martin Love and this guy en vogue currently. And again, this is my interpretation of this, but the main theme of constructivism is that in order to have a proof, you need to be able to construct it. And one way of seeing this is that evaluation is only successful if it doesn't result in absurdity. So if you are able to construct the expression, so then it stands. That stands. You've been able to construct it, therefore you have the proof. For instance, 2 is less than 1 should be impossible to construct. Basically, you shouldn't be able to evaluate that, which is a bit against our mainstream languages where that expression is perfectly valid. It just gives us the false value of a Boolean. So it's not a big deal. It could be returned either true or false, and that's fine. But I think that causes issues like Boolean blindness, and we'll talk about that during this talk as well. And quickly, just an example, one intuition about the constructive function, for example. We can create a constructive smaller than 1. So this could be smaller than 1. We have 1 and 2. So let's do 1 is smaller than 2. We see you can construct it. But if we try to do 2 is smaller than 1, oops, collapses. We are unable to construct it. So ideally, this is what we would like to achieve. So this is blow up the evaluation. Obviously, this is LambdaConf. We believe in statically typed languages, so the type checker won't let us blow up during runtime. But for the moment, take this concept that 2 is smaller than 1. It's a bigger deal than a Boolean. It's something that it's absurdity. So we shouldn't continue that branch of execution, or that branch of evaluation, or that line of thought, if you want to take it more philosophically. So enough about theory. Let's have a first contact with the syntax. We said we have predicates on variables. So we have the variables on the left. It's just an ID. Doesn't have any meaning. It's just a reference. And on the right side, we have a set of predicates, which I'm saying that, A is a member of NAT, and B is a member of NAT, meaning naturals. And obviously, NAT doesn't exist yet. It's a core calculus, so we don't have anything like that. That's something that we will have to build ourselves. And we'll do that during the talk. So we'll have NATs, but bear with me for a moment. Imagine we already built NATs. So we create a NAT tuple. And then we extend this set of predicates with another predicate, for example, for the ordered tuple. And we do that by adding a new predicate on A. And the predicate is it's a member of the set of smaller than B. Again, smaller than B is not in the calculus. That's something that we need to build ourselves. We'll do that again. But imagine we already have those two things. So below we see what's the end result of that expression. We see that A has two predicates. It's not just one predicate. So again, this is constructivism. Changes the mindset. It's not that we have a term that has a type because we say X is of type T because we labeled it, and that's the end of the story. It's just we have a value, we have a term, and it could be of any type. We just need to check it. It could be of T if it holds for the definition of that type, or it could be of some other property. So that allows us to add multiple predicates of different types. What we need to find is that those predicates are congruent. For example, we need to nat and smaller than b need to be congruent. Basically, it's a compatible set is either a subset or orthogonal, so we can have both of them, and that will be valid. But if we then add another one saying A is whatever, it wouldn't hold. So yeah, I think that's quite a key property as well of structuralism, because we don't care how we build this. We don't care if we added not tuple union with that, or we've written order tuple below directly. We don't care about the provenance of this object. We care about its own structure. And as FP developers, we know that the importance of local reasoning, how much easier, how much powerful FP is because of local reasoning. So this kind of gives us local reasoning at the type checking level. And that's why I think simplifies the calculus type checking using a structural typing. This is in line with propositions as types. So there is an isomorphism between X is a member of P, or X holds for property P. For X, property P holds. So the syntax I've chosen is the one on the left. X is a member of P, a set P, but meaning that that set is the set of all the values for which property P holds. So as we mentioned that we are using predicates, so that predicate need to hold for that value, and that will be a member of that set. So it's we add in a bit more cognitive load of the definition of the membership to a type, but down the line, I think that helps with the reasoning. It's not just that we say that X is T axiomatically, but we need to provide a proof that X is a member of P. And so in the example before, nat and smaller than b were both predicates, therefore both are types. The distinction gets blurred in a way. A bit more syntax and semantics of the calculus. We've seen the union in action. Let's recap. If we have the order tuple again, we created another refinement of this set by adding a predicate saying b is equal to 5. Again, the syntax of 5 doesn't exist, but imagine we have a syntactic sugar to imagine the provided we have nuts already and syntactic sugar for 5, so that's what we can write. So again, the example with this will be that now b is fixed to value 5. So when you unify, you'll have that b is a member of nat and is equal to 5. So both are, the equality there is not a assignment to variable b, is just a predicate of equality, which again I won't go into detail. It needs to be an equivalent relationship, and equality it's complex, especially with subtyping, but I won't go into much detail. Just think that this is just a predicate that's saying that there is a membership. So think about the equality as syntactic sugar for b is a member of a set of equal equivalence to 5. So we have now bounded by 5, and again this is the end result of these operations. Yeah, as I mentioned.
Question.
Yeah.
What is the relationship between these lines? These different predicates, you have A, a member of nat, B is a member of nat. Are those being ANDed together? Are they? I don't understand the relationship between those lines.
Well, these are elements of the set. So the thing is that you can add multiple predicates on the same variable. Then you need to.
So this is the conjunction of those predicates?
Yes, exactly. Yeah. Yeah. It's basically a product of those. It's an intersection, conjunction. Exactly.
So what is the, when you say order tuple union with b equals 5, order tuple represents a set that has all order tuples in it?
Yes.
And then b equals 5 represents a set, the set of all...
No, it's only one.
where
Yeah,
b
but it's only one. The power set of that is only one element. It's 5. It's we'll see when we construct nuts. We'll have a probably better intuition.
So this is a set.
Yeah, we'll see.
B equals 5 already in order tuple, or
You add to the set before, and then you have the result below. But again, you could have written it directly. We'll see more about creating natural numbers after. Sorry, there was another question.
I'll wait.
Okay.
Yeah. So how does the scoping of these things work? Because you mentioned B, and so the B you add in order tuple. You already have a B, and then you say B equals 5.
Yes.
So, like for example, here when you added A equals less than B,
Yeah.
what would happen if B is a nat wouldn't have been added beforehand? So, I mean, you seem to
Yeah.
create these names.
Yes, I mean that's definitely the scoping of that. You could infer that needs to be a nat, but I'm expecting that at this level of the basic level, it needs to be there already, because if you create a property of B, you need to.
If it's inferred, then it means that there was some kind of hidden memory.
No, well, I mean that's something that you could infer, but there is no inference in the basic calculus, so it probably will be the scoping will fail because there's no B in that scope.
Okay.
So first you need to add the B. It's a member of nat.
Any set, you need to have a set which has the proper scoping.
Well, it's union compatibility, isn't it? That's got the label B and that's got.
Yeah, yeah. I mean, it is a nested scope. So if there is a B upper, it will go up in the basically a chain of nested sets. You can see as a tree.
Yeah, no, because I mean, usually a set is thought like something without an order, and this sort of implies there is an order.
Yeah.
You have to.
There's no order. There's no, but the order. There's no order there. You could add them any order. It's just it needs to find. You are adding a reference to. So when you say B equals 5, that's fine. You don't need to have anything. B equals nat. You don't need to have B equals that beforehand because you're adding B equals 5. That's fine. But when you say A is smaller than B, obviously B is a reference. So it's on the right hand side. So you need to have some B defined somewhere else. But when you say union with B equals 5, the B is basically created fresh. If it's not there, you have it there. If it was already there, it was going to be a predicate. You need to unify. If it wasn't there, that's fine. You introduce B because it's fine. You say B is equal to 5, okay, fine. If that's the only fact you have, you believe in that. So that's an introduction rule because that holds always. If that's the only information you have about B, always holds. Okay, but what happens if we are asserting the unknown? Imagine we have a set where y is nat, and now we union with A equals y. So the compiler should disallow this because at runtime it will fail because y could be anything. It's unbounded. So we need. If we make the predicate, if we make it smaller than something that blows up evaluation, if you do this, the compiler needs to type check that there's no proof that y is smaller than 5. So this is a compilation error. So this is how it looks like. So we see that there's no guarantee that if we don't do that type checking, which I haven't added that, probably that will be something that I'll add after the type checker. So the first type checker will blow up. It won't care about. It will be dynamic typing. So this is dynamic typing. This is like the error in Haskell or require in Java or Scala. So we introduce an invariant in our program, but that's unsafe. If we go to runtime, if the invariant doesn't hold, it will throw an exception or error. So the thing with the dependent types is that the type checker, the compiler, will require you to have the proof that holds. So how do we achieve that? So this is the co-product. This is one of the reasons why co-product being in the meta theory as first class, the same as product, gives us leverage to allow the blowing up of branches. So in this case, we have two branches. We do the smaller than of y is smaller than the b on. So now we are using dot for accessing one of the members of. Well, sorry, I'm going a bit too fast, but there's a lot to go through. But I created an alias bb5 for bounded by 5 just for readability, and then I'm creating. This is more like a traditional math. So the value on the left is returned if the condition on the right holds. So we are basically executing the predicate. So if in this case it's safe to blow up. So if this branch we find an absurdity because y is something that is bigger than 5, so that branch dies. But we have the other branch that must succeed. So it's again another job of the type checker to make sure that all the branches in a disjoint union is properly disjoint. There's only is basically check the logical predicates there to guarantee that there is only one branch that will continue in one case. So then the type checker can remember that this has been checked, or well, that's an implementation detail. If it doesn't remember,
Middle line.
yeah, sorry, it's just for separate. It's
Okay.
empty. Sorry, yeah. You could add more cases, but in this case we only have 2. But I created a line just for indentation. So I think this constraint using being very strict about invariants has a huge value for our software development. Not only now, this might sound academic, but I think it has implications with our day-to-day software development jobs in business, in day-to-day businesses. We use Booleans, and we have a lot of logical checks. We have ifs. We combine those Booleans, but this has the issue of the Boolean blindness. What does it mean? Is when the predicate, well, the if or any comparison returns a Boolean, you discarded basically what was the fact that you checked. You only get true or false. It's just a bit of information. We discarded what was the logic behind that check, which is a bit unfortunate. The developer needs to remember what was the Boolean about. You only have the name of the variable, which doesn't have any semantic value. And if you combine different true or false, what's that intersection? Again, that's something that you need to keep in your head, which I find it a bit unfortunate when you have a compiler which is so great at remembering facts, and the facts that come from logical properties and logical checks are discarded. And it's your job to remember them. So I think dependent typing using decidable types is something that might improve that a lot. So we want basically invariants enforced by the compiler. We can make those predicates, those invariants first class. And some languages have started introducing refinement. So that's one way of introducing an invariant, have a refinement of the type. So the line between what's a type, what's a refinement, what's a a number or a type plus some invariants. Gets a bit blurred. For me, all of them are types. Just if you constrain the domain of the type with an invariant or a refinement, that's another type. It's just a different domain. This happens, for example, again, well, decidability. It's an overloaded name, probably not. I use that because that's what Idris uses for this kind of concept of having a type defined by a predicate. It has a decidable equality, decidable something. So, but again, in type theory and compiler theory, it's overloaded. So don't. The main thing is that there are no constraints that you formally verify. I want to emphasize on the business value of these invariants. We can create types based on predicates that are simply the Boolean checks that we already make. If we were able to lift them into invariants, into types, so we will gain that power. And Idris started to go in that direction. The Stacc calculus is mainly focused on that. Everything is a predicate, and those predicates give you a type. So also this could be seen as pushing the invariant check into the caller. So the function logic is shrinked, the domain is shrinked because you are adding an invariant to the signature of your function. So when I'm talking about optionality here, I mean implicit invariants where, for example, we have a clear example, a square root. If you had a principal library, it should be from double to a maybe of double or option of double, because it's not total. There's no totality there if you pass a negative number. So unless you have imaginary numbers with reals, so it's not a total function. But instead what we do is from double to double, happy days, and wait for the surprise, because what will happen is going to be an exception, not a number, depending on the language. You had a question. Yeah, so that's basically not ideal, because it's a PagerDuty call at 3 a.m. waiting to happen. I've seen errors in my current application because not a number, because in Scala it doesn't throw an exception, so then the not a number gets to the end of the wall, and who knows where did that originated. But anyway, this is not good. So if we push the optionality to the caller, we should have instead a shrinked domain where we only have from non-negative numbers to non-negative doubles. So this function now is total, and we haven't only shrink the domain, but we also have shrink the codomain. We can return the information that this is a non-negative double. So if the compiler is clever enough, so that information will be valuable down the line. So this is usually new types, gives us this functionality. Opaque types in Scala. There have been talks about that. Well, probably most of you know new type is just a way of aliasing a type, but making it different at compile time. But totality is only part of the solution, because we saw how the totality it's very relevant for FP. But there are more subtle problems with with total functions. We might have implicit invariants that are hidden. For example, if we see a signature like get invoices from a list of order to list of invoice, I would expect that there must be some filter inside, because if it was one order, one invoice, you will have order to invoice and map that to the list of orders. So something is going on there to require list to list. Wouldn't be much better if we made the invariant explicit. So we had, this is pseudocode, the current syntax is not, but there could be a syntax in a language based on Stacc where we are adding the invariant to the signature. So now we have just a function that gets an invoice or gets an order, but only if there is certain invariant on that order, and then we return one invoice. So it only gets orders that have been fulfilled that can give return an invoice if you apply this function. So now this function can be mapped to a list of orders that honor this invariant. So again, we pushed the optionality to the caller. You might say, well, it's just moving the invariant checking from one side of the call to the other. But as with every process that is directed, if we trim down, if we tidy up upstream, there is a multiplier effect. And downstream gets much neat, gets more cleaner, is more reasonable. I think the power of this can be quite important. We mentioned that the way to add invariants, currently the mainstream way to do that is with new types.
I have a question.
Yeah.
So does the compiler help in telling you that you need to pass the constraint to the caller?
Yes, that will be, I mean, this is pseudocode, but it will be a set where there is an O or order, and you establish the predicate of whatever fulfill order into on O.
And
Yeah.
if you have only the first case,
Yeah.
like the one get invoices order list of order will still
Yeah.
invoice. Can the compiler help you by telling you, hey, you need to have
Well,
predicate over here, because there are type-based cases here that tell you that you could have a problem.
I mean, I don't know if you are doing an invariant check inside that function and the compiler is clever enough to identify that the only code path goes to that invariant, it will give you a warning, push that invariant to the signature. I don't know, I'm just speculating of my ideal compiler what will do. But my point is that we are making an invariant implicit and we don't know what's going on from a list to list. That's always a more difficult signature to reason about. It is much simpler to reason about a function from one to one, but make the invariant explicit, because now if we have a list of orders, this function now get invoice, you map it, but now you said only map it to a list that orders have this invariant. So this function now is neater, doesn't have to deal with filtering inside. It's more testable. You don't need to test a list. You just one-to-one, which is much easier. So we mentioned new types, but new types have shortcomings. Main one is we talked about intersection of types, and sadly, the intersection of types is something not easy to do in our languages. In Scala has some sort of intersection. I think in Haskell, I'm not sure. I think there is a way of doing it, but it's always fringe. It's not. If we want to do, imagine we have two properties. For one property, yes, we can create a new type. But if we have two, either we create a new type of A and B, or we need to introduce more ceremony. And ideally, intersection of logical intersection conjunction, it's a very important combinator, and I find it a bit sad that it's not available. I think it's something that we should improve. So just a reminder to keep an open mind, and I think we all agree that FP is the way forward, but there are things to improve, and I think that how make logic first class intersection of types first class and undoable can give us a huge value, because we do that every day. I mean, when we are, I think we internalized in our languages that we don't have intersection, and I don't know, in OO we create a new interface, or we start adding words into the interface, or we do a lot of, we create a lot of silly structure just to overcome this lack of, when we have two concerns that are orthogonal, for example, two predicates or two invariants that are orthogonal, trying to smash them into a single type is difficult in our languages. And I guess we create a lot of noise, and we make our lives difficult, or we don't make them explicit, and it happens again and again. And we are so used to that, sometimes we don't see that we are missing a way to clearly combine those orthogonal types, or two orthogonal properties of your value or your type. And let's go back to the example and let's start building. So we said that we didn't have natural numbers, and we didn't have a smaller than, and I said that we were going to build them. So how can we build them? What we have is the empty set, we have predicates on vars, on variables, and we have disjunction. For the naturals, we can use the piano encoding. For the zero, we said we have empty set, so it's an easy choice. We use the empty set for the zero. For a successor, we can say that we use the variable pred for predecessor. That needs to point to a previous number. So here I created a few numbers where you see pred on 0 is 1, pred on 1 is 2, and 2 in the two formulations, one referring to 1, 2 referring to 1, and the other just nesting the pred. So as I said before, these are equivalent, unified to the same. The references basically get only the variables are the important, not the names on the left hand. But how do we abstract over all the naturals? All those elements were finite, were just finite numbers. How do we create a proper NUT? We use the disjunction that we said that was available. So following the standard way of defining it, so we say it's either the 0 or the successor. This is fine. We say the successor could be any number that it's a successor of a predecessor. So this is no surprises here. But how do we define successor? Well, we need to welcome inductive types. And the way to create induction on the Stacc calculus is by creating loops, by referencing. For example, we have a successor has the predecessor, and the predecessor needs to be a member of NUT. So there is a recursive reference there. There is a cycle. That's how you create inductive types. Just one note, I use colon here, but it's the same as membership. I think in the syntax I made both interchangeable. I think colon is more readable, and basically people will get angry. After the double colon outrage with Haskell, I wouldn't dream of just requiring membership. But I use a membership during the talk. I think it's more theoretic, but probably I will just colon all the time. So yeah, pred is a member of NUT, and NUT we say that it's either 0 or successor, so there is a loop there. So the problem is always introducing recursion could be unsafe, but in this case we are only on the realm of data. This is a fixed point, so this is structural recursion. We said that the predecessor points to an already existing natural number, a natural construction. So we are just adding layers, which is basically what is the nature of induction. That natural is a non-inductive type, and we see that, and this is safe and gives us a solid foundation for defining data. We see this more graphically. What we have on the left is the description for naturals, and on the right we have the number 2. On the left we see that the dashed lines are a choice, the disjunction between, we can substitute NAT either by the terminal object empty set, which we said represents 0, or we have successor, which has this variable predecessor pointing to a NAT. So we see this must terminate because it's either you keep going on that loop or you end in the terminal object empty set. So there's no termination problems. If somebody keeps looping to the infinite, it's simply a term that doesn't enter. It didn't enter the system. So it's always well formed, as we see on the right. And another thing that I didn't mention in the calculus is I didn't introduce any syntax for what's a type or what's not a type. Both are defined in the same way. And if we say 2 was just a set of variables, and NAT is a set of variables. But which says that the thing on the left is a type, is that the cardinality of that graph is more than 1. We see that because a power set of that structure you can have more than one path. Instead, on the right, we only have one path. It goes from 2 to 1 to 0, and the cardinality of that structure is only 1. So that's a value, and the thing on the left it's a type. So yeah, you can think of decision trees or grammars, and they look the same, and not a surprise because a grammar is to parse some text, parse sentences, and a type is to generate sentences, generate tests with certain structures. So it's a dual. What you use for parsing, you can use for generating stuff. Again, realizability was mentioned in the keynote last night. That's a fascinating concept. We only have 5 minutes, so just an idea that the way we talk about successor in traditional languages is a function from NAT to NAT. But I think this is too powerful. NAT to NAT could be never terminate, could be adding 2. We don't have any guarantee that it's going to be the successor. So I think it's not a proper representation of an induction step. So maybe we need a different signature for induction steps, or I don't know if anybody knows any pointers of research in that area, or so please share them with me. Just an idea. I think it's important to have induction as separate from morphisms that can go anywhere, because induction it's well formed. So we said that we had to create our own constraint smaller than. So quickly, we have A is equal to natural, B is a member of natural, sorry. And then we have these results. It's basically the syntactic sugar for implication. And we have a disjunction there. And we have 3 cases. In the first case, if A equals 0, B is not 0, we say that we return empty set 0. But that doesn't matter. When we use the smaller than, we are only interested whether that constructs or whether that results in absurdity. So we can return anything really, it doesn't matter. But on the other hand, the second case says that if B is equal to 0, then we know that that property doesn't hold. It cannot be A smaller than B. Therefore, we need to blow up the evaluation, as we mentioned. And the way to do that in the basic calculus is by, there is axiomatically defined that empty set member of empty set, or anything member of an empty set, it's absurdity. So this will basically stop the execution, and this didn't construct. And the third case is simply the iteration call smaller than again with the predecessor of A and B. So it will carry on until calling itself until you either get to first case of success or case B of absurdity. Again, you could say this is the same as returning true or false, but there is this thing of the compiler. It stops execution and it's not simply a value. It's not a valid value. So yeah, some things that using your booleans as predicates and invariants is fine. Go quickly, parametricity. The way to do parametricity in the calculus is we have a special set which is named set. This is inbuilt, and anything that is a member of set needs to be a set. So we can, an example is to create lists. In the list, we have the predecessor to another list. We have an element which is a member of T. We say that T is a member of set. So we can fit any kind of type in that T. If we look at that, we'll see a resemblance to some structure we've seen before. I even left the pred there instead of the usual tail for cons. So we see how it's the same shape as the naturals. And this, there is the naturals and list adjoint, where we see that the share goods, most of the structure is shared, and the element on each cons. If we forget about that, we simply have a series of objects with a cardinality that equals the number. And a cool way to use this adjointness is using subtyping. And as this is a structural typing, it uses subtyping, arises naturally in the calculus. It's similar to how row polymorphism works in some languages, but so imagine we have equal nuts, which A is a member of nut and B is a member of nut, and then we say the property that A and B are equal. So it might seem a bit of a tautological invariant. Why do we do that? So one way of using this is, for example, if we want to constrain the size of the list with a particular size. So we have size is a member of natural, and list is a member of list, which we already created. And then we declare the invariant that size and list are equal nuts. So what's happening here? How does this type check? We said that list is a list, and now I'm saying that we pass list to B, which I said that B is a natural. Well, if we see concrete values terms for these two types, we'll see the adjointedness. So on the top of the slide, we have the value 2 that we are passing to size. So we saw that 2, we create a predecessor of 0 and a predecessor of that. That's 2. And below we have a list. And again, now I introduce something new. Imagine we have a string, and we have a syntax for adding a string literal. Well, that's something that you should create yourself. It's not in the calculus, but let's imagine we have that already. And I'm having a list and a natural, so you could have a list of characters. So, but imagine we already created the string, but this is simply to have some values on the list. And on this second structure, we have a list which the T is a string and the element is foo, and then it has a predecessor, it has a link to another cons, which is again T string, the element is ba, and the predecessor is the empty list, which is the empty set. And if we see the graphical structure of those two terms, I shaded the shared structure, and on white is basically the additional information that the list carries, which is there are two strings on those two cons. But there is a direct equality between a subset of the structure. And because we only care about the edges, because the shaded objects are simply a set that has a variable named pred and is spread everywhere. So type checks that the list is a subtype of NAT, because the only thing that NAT has is a pred on an object that it's either an object with pred or an empty set. Because I use the same name for tail and predecessor as pred, and because the terminal objects are the same, the empty set, you can find that if you traverse the structure of the types that we saw before, this should type check that we've seen that a list is a subtype of NAT. Is this adjoint?
Validate that the foo and bar of the same type, because the value
Okay.
could have been an integer.
Yeah, that's a good point. That's an H list. So exactly the cons could be of different types.
Yeah.
So this is an H list. So I added the same for not introducing more information, but yeah, you're right. Any element could be of type list. It is easier to create an H list. If you want to create a list of only one type, we will need to create another predicate saying that the type of the predecessor is the equal of your type. And that will mean that the empty list, the nil, will need to have a type as well. Right. So yes, that's a very good point, but shows that an H list is an easier construct than a normal list. So it will need more predicates. So yes, but it will still type check because the predecessors in the structure are exactly the same. If we forget about the element. And because it's a structural typing, if NAT only has a pred and you have a pred and this either another structure with pred and empty set, it's basically the same type. Yeah, higher ranks is basically we create more hops in between the membership of a set and that it's itself a set. So we create a layering of ranks, but that's obviously the inference of that will go out of the window, but still is not in the calculus, it's just theoretically. And identity is not interesting. We just see that we union ID with the T being equal to NAT, so we apply exactly the same, the type on T. We apply as any other value. So for the calculus is the same, having a set or a value, you apply, so the distinction gets a bit blurred. So it's already close to end, so thank you very much for attending. First I'll publish the talk in GitHub in that direction if GitHub's still there tomorrow. And the actual type checker to prove, because this is only on paper, so I need to prove that this works, and I'll add the type checker and the REPL with this calculus that at the moment is built with Scala, and I'll upload that shortly. So if you are interested, Landerl on GitHub, and Twitter, just give me a shout and I'll announce when the type checker and gets published. So thank you very much.